All right, it's working. I will begin with a word of prayer. Dearly Father, we thank you for this weekend and for the beautiful weather outside, and I thank you for these students. Just ask that you to help us to use this time, Lord, to glorify you and to answer any questions that remain for the students before test 2 here, Lord. In your name I pray. Amen. So ask away. It's up to you guys.
Question 5. We never got to do that.
Question 5? Sure, we can go over problem 5. So there you're supposed to graph. Let me just steal this here for a second. We're supposed to graph y equals to f of x minus 2 times x plus 2 squared divided by x plus 6.
Yeah, we still train together. Here and there's someone that can't make part of it.
All right, so what's the first order of business here, guys? We identify critical numbers, right?
Yes.
Identify x equals to, say, minus 6, 4, and minus 2. These are critical numbers. Right, and in this, yep. How would you factor it? No. Because x minus, I mean, the only way I can factor, I can factor x minus 4, but you're not going to like it. Right, but you don't want me to do that. Yeah? So we usually say it can't be factored in the sense that you can't break it into a smaller product of polynomials. If you did x plus 2, x minus 2, when you multiply that out, you have an x squared, right? So generically speaking, whenever we have x to the first power minus plus a number, something like that, that's already irreducible. Like linear factors cannot be broken down unless you leave the world of polynomial algebra, right? And this, thankfully, is not allowed in this particular part of the course, right? Like, we don't do this. Not for now. There is a place in calculus where that matters, but that's not our context, okay? So I should have just told you no and not even written that on the board, but you gave me an excuse to digress, so I seized that excuse. Yeah?
When you were identifying your x values, so why don't we do anything with the negative 2 and 4?
Because that doesn't make the denominator 0 or the numerator 0. So, I wouldn't say we pretend it's not there. We just have to take it. We take it into account elsewhere.
Okay.
So the larger point here is both of these cause division by 0, right? And I would say unopposed. Did I spell it? Anyway, maybe there's 2 S's in that. Whatever. Unopposed, right? There's no balance of x plus 6 or x minus 4 in the numerator, right? They're just in the denominator. What does that mean? That means x equals to minus 6 and x equals to 4. These are going to be vertical asymptotes, right? Now minus 2, what happens with that? What's that do? This one right here, minus 2, this makes numerator 0, right? If you plug in minus 2 into the numerator, you get 0, right? So the overall expression is 0. So this implies that minus 2 comma 0 is x-intercept of graph. Right? So This one's relatively easy in the sense that there's no overlap, right? There's no interplay between the numerator and the denominator. It's just straight. That's an x-intercept, and those are vertical asymptotes, right? So that's what we have to look forward to as we graph it, right? Now the next step to make a careful graph is to draw a number line. And if you look at the quiz paper that I gave you, there's a place to write a number line above the graph, right? So I would encourage you to write it there. So I'll write it up here. So which comes first on the number line?
The negatives.
Yeah, the -6 comes first, doesn't it? Let's see here. So we go, let's say -6, then -2 perhaps, and then 2. That would be 2. Yeah, you're right. 4 is the next interesting thing here. Here's 4. I shouldn't mark that, right? Okay. So those are your critical numbers, and we know that the sign of the function can only change from plus to minus at those numbers, right? So we just need to check the polarity, the plus or minusness of it, if you will, at each one of those things. Now the -2 matters, right? So like, for example, try, I'll write it over here, check f of 0. What's f of 0 equal to? We get what? -2 times 0 plus 2 squared divided by 6 times -4. What you got? You got apparently looks to me like a 2/6. So you got a 1/3, right? So apparently the y-intercept is 1/3. The larger point here is it's positive where 0 is. Where is 0? It's between -2 and 4, right? So I could plus up here. And then what's the nature of the, well, we have a bounce at 2, right? A bounce at -2, rather. So the sign does not flip there. The sign stays positive over to here. But then at -6, power 1, right? So we flip from plus to minus. Now, on the other hand, at 4, there's just one copy of it, right? So I flip from plus to minus over here as well. Right? What? Because they've got an x plus 2 squared here. If the total number of factors corresponding to the critical number is even, it bounces. So like if I have, one x plus 2 upstairs and one x plus 2 downstairs, that would keep it, that would keep the sign from changing as you go across -2. If I had, if you could imagine, if I had 3 x plus 2s upstairs and I had 1 x plus 2 downstairs, the net total of the factors would be 4. If I have 4 factors, it'll bounce. If I have an odd number, like if I had 1 factor upstairs and 2 factors downstairs, again, I would have a sum total of 3. It would cross. It would change from plus to minus as you go across that factor. It's 0. So it's the same pattern that we saw before with polynomials. It's just now we have to count the net number of factors above and below, all right, rather than just in the factorization of the polynomial. The other thing I need to worry about is what's the horizontal asymptote, right? So notice here, that's relatively simple because if you look at it, we've got, what's the degree of the numerator? It's 2, right? What's the degree of the denominator? It's 2, right? So if you look at it, what do you have? You've got, -2 times x squared plus 4x plus 4, right? And you're dividing by x squared plus 2x minus 24. The key point here is if you look at the expression, the leading coefficients are what? You got a -2 over 1 here. Remember, we had a theorem when the degree of the numerator and the degree of the denominator are equal. We can just take the ratio of the leading coefficients. That gives us the horizontal asymptote. So therefore, y equals to -2. This is my horizontal asymptote. Now, if you want to, you could do long division here and find the same, all right? Do you want me to show you that? Sure. All right. So we've got upstairs minus 2 times x plus 2 squared, so that is actually minus 2x squared minus 8x, yeah. Yeah, minus 8. So I'm just multiplying out, this right here, guys. And then we're dividing x squared plus 2x minus 24 into that, yeah? And how does that division go? It's kind of a boring long division in some sense, because it doesn't, there's not much to it really. There's just one step kind of. But the first step is, how do I get a minus 2x squared from the blue? Negative 2, right. And then you're done. Almost. I mean, minus 2, so I do minus 2 times this, it gives me minus 2x squared minus 4x plus 48. These details don't really do much for us in terms of the graph we're about to make, but I'll finish them just for the sake of the long division. So I get minus 8x plus 4x, which is minus 4x, minus 8 minus 48 is, I think, minus 56. So that's your remainder. So what this means is that minus 2x squared minus 4x plus 48, excuse me, my bad, copied the wrong one down. If you don't mind, let me go back to the before we multiplied it out, okay? Let me go back to before I multiplied it out. So what this means is that minus 2 times x plus 2 squared divided by x plus 6 times x minus 4, right? This is actually equal to minus 2 minus 4x plus 56 divided by, well, x plus 6 times x minus 4. You know, you can keep in mind that x plus 6 times x minus 4 is actually equal to x squared plus 2x minus 24 if you're fuzzy on why I wrote the fraction of it. Anyway, the larger point is just this. If that's how the long division works out, what happens is x goes to plus or minus infinity. So this piece goes to 0 as x goes to plus or minus infinity, and you have y is approximately just equal to minus 2. That's your horizontal asymptote. That's what the function looks like in terms of the large scale behavior of it, all right? Like I was just saying, you don't have to do all this. When the degree of the denominator and the degree of the numerator are equal, there's a nice shortcut. The shortcut is simply to look at the leading coefficients and take their ratio. So the leading coefficients of the top is minus 2. The leading coefficient of the bottom is 1, so the horizontal asymptote was y equals minus 2. All right, so let's get the graph going here. So here's my handy dandy y-axis, and here's my x-axis. Let me put in my vertical asymptotes. I usually try to make those dotted lines. And over here, you got one of them. I also know that I have a horizontal asymptote of minus 2 here. Right? And what else do I know? Let me put some labels in here. So minus 6, 4, minus 2. So you guys told me where was the there's a x-intercept, right, at minus 2, 0. So we know that the graph crosses the x-axis like right here, right? And we also know, well, I say crosses, but I really should say it bounces there. And there's also, I also calculated the y-intercept right here, right? Because we calculated f of 0 as a third, we know that 0, 1/3 is on the graph, right? So, yeah, roughly speaking, it's something like, I mean, by no means quite this. This is very crude, but right there, something like 0, 1/3 is the y-intercept. I did not ask for that in the quiz, but if you put it there, it would have improved your graph, right? Okay, then what? Then we just follow, we can graph, okay? So we've got vertical asymptotes, which means the function either has to blow up or blow down at those points, right? And the sign chart tells you which to do. So here, and horizontal asymptote means that you're going to that eventually. So it looks something like this here. It's negative. Up here, it's up, it's blown up. It comes, it bounces, and then it kind of goes up like that, something like that. And then it's negative over here, and it's asymptotically going to -2. So it's got to look something like this. And there you go. That's the graph. So an interesting follow-up question to this would be, what's the range? I didn't ask for this on the quiz, right? But here's an interesting question. What's the range of f of x? That's a question you could answer with the work we've done. It wouldn't be hard. Yep.
Infinity to -6, non-infinite, or -infinity, sorry,
Minus infinity to, remember range is the y values though. It's okay.
-2 then.
To -2. Is -2 included or excluded? What do you think? Excluded, yeah.
And then you have union,
Mm-hmm.
so it's going to be 0.
All right, is 0 included?
Yes.
Yeah, it is, right? Because it bounces off the x-axis. That puts 0 in the range. And then you just keep going on and on and on, right? So there you go. There's the range.
If it's positive between -6 and 2, why is it going down?
Well, it goes down, but it didn't get past the x-axis. Positive doesn't mean increasing. Positive just means above the x-axis.
Oh, true.
To tell where the function's increasing, we need to look at something called the derivative. And if the derivative was positive, it would be increasing, but we don't know about derivatives, right? So we can't do that. Other questions? Yep.
If the -2 wasn't there, would the horizontal asymptote be 1?
If the -2 wasn't there, and you're saying I just erased this,
Yeah.
then what would happen is the graph would turn upside down. Like this would be down. These would be up, and the horizontal asymptote would be 1 up here. I mean, let me just graph it over here for you. Without going through the work, I can tell you from what we've just done that, yeah, the graph. So you're asking about what if you had y equals to x plus 2 squared divided by, what is it, x plus 6, x minus 4. So just the same, but without the -2, right? So pretty much a lot of things stay the same then, right? You still got your vertical asymptote at -6. You still got your vertical asymptote at 4. You still got to bounce at 2, -2 rather, right? But the difference is now your horizontal asymptote is actually at 1. And instead of the sign chart flips over actually, and you get something that looks like this basically. It would be like that if you went through all the details. So it's kind of the flipped over. So yeah, multiplying, and I mean, so yeah, I mean, you could, if you were really, really good on your transformations of graphs, you could see that if you take this graph and you flip it over the x-axis and then you stretch it by 2, you get the other picture, right? Because it is taking the function and multiplying by -2, right? Multiplying by -2 corresponds to reflecting over the x-axis and then stretching by a factor of 2 for what it's worth. I don't know, I'm just graphing it from what we did over there, really. I didn't use the transformation idea. Other questions? Would you like to see me do more completing the square?
Yes.
All right. So, choice is up to you guys. Give me the quadratic you want me to do it on. can take it easy on me and make the leading coefficient x squared. I mean, don't all speak at once. Anybody?
I just don't know why you're supposed to do it. I'm just completely confused.
We can do it on any quadratic. Any quadratic you can do it. Just make up numbers. Give me any three numbers. 5x squared plus 7x plus 9. All right, this is going to hurt a little. So because it's going to have fractions, but we can still do it. So the step number 1 is to pull the 5 out. We do that like so. All right. Next step, take, what's that?
She just told me we should do that one instead.
Well, we will do that one next. How about that? We'll do an easier one next, okay? Because the lion's share of times I test you guys on this, I don't besiege you with the leading coefficient not being 1, do I? Not usually. I'm nicer. Tell my children. Let's see here, 5. So x plus, what's a half of 7/5? Well, it's 7/10, right? Divide 7/5 by 2, you get 7/10. So we do 7/10. You square that thing, all right? At that point, you've added 7/10 squared. So to be fair, you have to subtract 7/10 squared. 7/10 squared is 49/100. 9/5, let's put it into hundredths. In terms of hundredths, 9/5 is 180 hundredths, I think. You chose the wrong. It's okay. This is something you guys should be able to do. I don't expect you to be able to do this one quickly. I think this is probably going to take you guys 10 minutes, but you ought to be able to do it. I do give you a formula sheet, so you could like literally write down this example and like model your work on this example, for example. What's great googly moogly. Brain not working. 131, I think. What does this tell us? What do we find out at this point? We find out that this polynomial is prime. Because when we complete the square, we got a plus. Prime means you cannot factor it with real numbers. Right, so if we wanted to factor this with complex numbers, we could do that. It would look like this. But of course you can simplify that a bit, and you can simplify this a bit, and you could rewrite that as like 5 times x plus 7 plus I root 131 over 10 x plus 7 minus I root 131 over 10. Now it's factored, right? But the thing is, the factoring required what? It required complex arithmetic, right? So if we're just allowed real factoring, then we say that this is prime. What's the vertex? If I say y equals to this, 5x squared plus 7x plus 9 has vertex what? Where? With what we've already done here on the board, it's easy to figure out. All you got to do is go back up to this step up here, all right, and trade it for y is equal to 5 times x plus 7/10. And when I multiply 5 times 131 over 100, 5 over 100 is what? How many 5s can you put into 100? I think 20, right? So we got plus 131 over 20. And if you look at that, we can see the vertex from that formula. That's the vertex form of the parabola. What is it then? So the vertex is at minus 7 over 10, comma 131 over 20. So there you go, that's the vertex. So I should have not given you guys the option to make the leading coefficient something other than 1, right? Because that makes this calculation much, much harder.
Yeah, I have a different one for you.
You have a different one for me. Okay, here we go.
Yeah, x squared minus 8x plus 11.
Plus 11. All right, there we go. So this one, this time we don't have to factor the leading coefficient out, right? That makes it like way, way easier. We just take half of minus 8, which is minus 4. You square that, right? Now, by doing that, I get back my x squared, I get back my minus 8x, but I've also added 16 if you FOIL that out. So to be fair, I must subtract 16. And then I add 11. And if you, so maybe you added 16, right? Was that it? No.
Put the x on the outside.
A lot of people add 16 here. Sometimes that's a mistake I see. That'll work against you. But then we've got x minus 4 squared minus 5. If I was interested, where's the vertex? Like, where's the vertex? So this shows me that if I look at y equals x squared minus 8x plus 11, which by the way is equal to x minus 4 squared minus 5, vertex where? At 4 comma minus 5.
So it's a positive 4 because why? Why did you say it was
Because the vertex is where the y value is smallest, and the y value is smallest when we make this term go away. So to make this term go away, I have to put x equal to 4. Like, more generically speaking, the vertex form of the parabola is this. So if we're comparing to this form, if you have a minus 4, that makes h equal to 4. The vertex is at h comma k, is the notation we used. So that's it. That's completing the square, right? But we're also interested in factoring. Can we factor this? Is this one prime? This one is not prime, right? In contrast to my horrible, ugly other example over here, which was prime, and we had to do complex factoring if we want to factor it, right? This one is not prime. And we can just do x minus 4 plus the square root of 5, x minus 4 minus the square root of 5. That's how that factors. Yeah? Oh, what are the x-intercepts? So we've factored the polynomial, right? And so this shows me that if I look at y equals to this, right? That graph, so y equals to x squared minus 8x plus 11 has x-intercepts of 4 minus the square root of 5 comma 0 and 4 plus the square root of 5 comma 0. Where did I get the square root from? Okay, so going back to here, x minus 4 squared minus 5, this is equal to x minus 4 squared minus the square root of 5 squared. We think of this as the difference of squares. Like I told you guys day one, we're going to use this a lot. A squared minus b squared, right, is a plus b times a minus b. So thinking of this as a and thinking of that as b, we have x minus 4 plus square root of 5, which is a plus b, and then x minus 4 minus square root of 5. Again, the pattern here, what I'm using, is this is a, this is b, this is a, and this is minus b, you know? It's always this pattern. When we have a minus from the completing the square, we can factor like this. It may not be pretty, right? The the number that we get when we do the simplification here, it doesn't have to be a square, right? It could be 5. It doesn't have to be 9 or 4 or 1 or something pretty. Should we do another? Can I erase the evidence of this ugly one here? Yeah, okay. Do you guys need to see long division? Is that something we should do? I mean, it's up to you guys. Eh? Yeah.
I think on that homework last week, there was some problems where you gave us a graph with a hole in it, and then we had to find the polynomial of least degree. Something like that.
Oh, sure. You want to do find the formula for the graph kind of problem, right? That's a good idea. How about I have a vertical asymptote at -3, and suppose I have something like this. Well, I don't want to do that necessarily. Sorry, I've done it all in one color. My bad. But let's suppose that that hole is at like 1, 1/2. And let's suppose that that one's at like 2, 0. And let's suppose this over here is at, I don't know, 4. Find a rational function which has this as its graph. So my approach for solving this kind of problem would be to ignore the hole to start with and build something that does everything else. Because I know I can punch a hole in the graph by simply multiplying by a particular factor. Like, for example, if I wanted to go back to problem 5, right? And I wanted to punch a hole like right here at 1, all I'd have to do, this new function here, y equals to g of x, all I would do for g of x would be to use the formula for f of x that we worked on before, and I just multiply it by x minus 1 over x minus 1. That's going to punch a hole at 1. So like, that's just a trick. You know, if you want to put a hole in a graph, just multiply by this factor x minus 1 over x minus 1 to put a hole at 1. Think of it as a mathematical hole puncher, you know. We can do that. So the real question, the harder question is, how do you find a rational function that looks kind of like what I put up here? Let me start us out. So we're looking for y equals f of x equal to what? What do I want? Well, I mean, I'll start with the easy thing. I want an x-intercept of 2, 0, right? So I think I'm going to put an x minus 2 upstairs, yeah? Right? That'll get me that. There's one thing down. What else do I want? I want a... yeah, I need an x minus... I need this vertical asymptote over here, right? So that's x minus 4. So I'm not, I'm not doing them in any particular order here. I'm just, so okay, this takes care of the 0. This takes care of that vertical asymptote. Would you see why why did I put not a square but a first order? Because see the vertical asymptote's like crossing, it's flipping from plus to minus. That means that there's an odd power down here for that one. And so since I'm looking for like I'm looking for like the smallest kind of rational function I can that does it. So I don't want to put a cube there if I can get away with a first order. So let's keep a first order. X plus 3. Now there I don't have the luxury of doing just x plus 3 because it's a volcano, right? That means I need like an even power in the denominator to get one of those. So I'd have to have like x plus 3 squared there. Right? I have everything I need, except I haven't taken care to do what? Yeah, I want to put the hole in the graph, right?
Don't you normally find a full graph that has the numerator and the denominator has something in common?
Well, here the numerator has degree 1, the denominator has degree 3. The horizontal asymptote is then y equals 0, right? So that's good. But we can take this and multiply by a, right? We don't know what a should be, but just any number. You can put a number here, and that'll just kind of make it more steep, and basically just make it more or less steep. But it's the same generic shape. It just kind of stretches it out vertically, right? But you'd still have the same. If you stretch a rational function like this vertically, it doesn't move the x-intercept. It doesn't move the vertical asymptotes. Those stay put under a vertical stretch, right? So it doesn't matter what I put a there as long as it's non-zero and positive. I do need positive probably. Well, I don't know. Hold on a second. Does this have the right sign properties? I don't know. What happens if you plug, like, 5 into it? You get plus, 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 right? So we want positive there, which means that I do need a to be positive to make that work. All right. So yeah, a has to be positive to make it look like this. Like the same formula with a negative would do what? It would just flip everything on this graph upside down. If I had a negative, it would look like what I'm about to graph in green foolishly. It would look like this if a was negative, yeah? If a was negative, it would look more like this, yeah? That would be a negative. But anyway, let me erase that. Yep.
So if there was no hole in the graph and we were to write the equation, would we just leave it as it is right now?
We'd need more information to fix a particular answer.
Okay.
You need a point on the graph in order to, like, if I said that the point 1 comma 1/2 was on the graph,
Yeah.
then we could,
Then we could.
yeah. So let's basically do that. What is f? We want f of, well, the point is, so guys, if I take this, right, and then I multiply by x minus 1 over x minus 1, that just punches a hole in the graph at 1. And the reduced function at 1 is going to be what I had right before I added the hole punch. And then to figure out what a is, I use the point that I'm given, right? I know that I want to have, when I set x equals to 1, I want to get 1/2 is a times minus 1 over minus 3 times apparently 4 squared. So that would give me a equals to, what you got here? Well, the minuses cancel, right? So I get 48 over 2, also known as 24. So there you go. Y equals to 24. X minus 2 times x minus 1 over x minus 4 times x plus 3 quantity squared times x minus 1. That is a equation whose graph will be the one that was given without, let me get rid of the green.
Okay.
Yeah, the green was a comment.
And that would be if the hole was a point instead of a hole.
Yeah, if if you had the hole in the graph at 1, comma 1/2. It's less important that you can do this specific problem than it is for you to understand the concepts that we ran across in this problem, right? Like, if we have 1 over something squared in the denominator and it's unopposed, that gives you a volcano in the graph, right? If you've got division by just a single factor, it gives you a vertical asymptote which has like a plus to minus kind of pattern, right? Infinity on one side, minus infinity on the other, or vice versa. If you have a factor in the numerator and it's not in the denominator, that gives you an x-intercept, right? And if it's not, so unlike problem 5, this one is just first power, right? So we have a crossing at 0. A crossing at 2, right? Whereas in the problem 5, we had x plus 2 squared, which means we had a bounce at minus 2, right? See the difference? So, but yeah, this is just a silly trick, though. This idea of, you know, take the function, multiply by x minus 1 over x minus 1. That gets you a hole in the graph. If you want to build functions with holes in particular places, you can use this trick. So a hole in the graph is kind of like, sometimes you're programming something, you know, in real life you might have the situation where the formula makes sense for everything, right? But there's just some kind of quirk or bizarre feature of your system that for whatever reason just refuses to allow that one input, right? For whatever reason the machine you have doesn't work there. And so like this models that idea that everything works according to this natural pattern. If that quirk, we could just get rid of it, it would just be the continuous extension of it. Just for whatever reason, there's that one annoying place where it doesn't work, you know. So. Other questions? I think that's it. So this is by no means comprehensive for the test, right? So make sure you study the quiz solution and, you know, things we've done before. Yep. Yes, sir?
I know this is like a ways out,